We had two worksheets that were due today. One was actually due yesterday, but we just didn't have a chance to check it. That was worksheet number 11, and then worksheet number 12 due today. We're going to check over questions 9, 10, and 11 for worksheet number 11 right now. Let's take a look at number 11 on worksheet number 11 here. Number 11 says an electron is traveling through perpendicular magnetic field of value 3.0 times 10 to the negative 1 Tesla. The magnetic force that it experiences is 4.5 times 10 to the negative 14. How fast is the electron moving? They tell me that the electron is traveling perpendicular to the magnetic field. That's a big deal. If the charged particle is traveling parallel to the magnetic field, what would the force be then? 0, right? If it's perpendicular, then we know that the force is going to be equal to QVB, and we know that we could find the direction of the force if we had to by using the hand rule for deflection. All of that stuff that we learned is valid if the charged particle is moving perpendicular to the field. Now, we don't know which way the particle is moving and which way the field is, but we do know they're perpendicular. So that's good enough to tell me that stuff that I learned here the other day is valid. We want to find the speed of the electrons. We're going to start off with that equation that we learned that is valid because they're perpendicular. F is equal to QVB. We're going to rearrange it to solve for V. I end up getting V is equal to F over Q times B. And then we're going to sub in our numbers here. Our force is 4.50 times 10 to the negative 14 newtons. Our charge, it's an electron, so our charge is 1.60 times 10 to the negative 19. We're going to drop the sign of the charge, right? Times the magnetic field of 0.300 Tesla, or 3.0 times 10 to the negative 1. When I do the math there, it should work out to be 9.38 times 10 to the 5. You know what? We usually, for a charged particle, get a speed that's 10 to the 5, 10 to the 6 meters per second. No guarantees. But when I get a 10 to the 5, like I'm relatively confident on that. If I get a 10 to the 10, I know I'm wrong because it can't be bigger than 3 times 10 to the 8, the speed of light. If I get 10 to the 1, could be right. Okay, the odds of it being right are a lot less, but it could be right. As long as I'm less than 3 times 10 to the 8. Usually 10 to the 5, 10 to the 6, though. Good. Next thing I want to do is an example number 2 that appears on the example question handout that I gave you a couple of days ago. We skipped by this yesterday as I had you watch that podcast in order to do the new material as some of us were working on the lab. We skipped by this one simply because it just didn't really flow with the material that we were doing yesterday. The question says a 5 times 10 to the negative 25 kilogram particle with a charge of plus 1e, which of course we know means 1 times the elementary charge, or 1.60 times 10 to the minus 19 coulombs, traveling north or geographic south through a magnetic field. Sorry, this should say magnetic south, not geographic south, magnetic south, through a magnetic field of 2.00 times 10 to the negative 5 Tesla pointing to the west. What's the speed of the particle that it must be traveling near the Earth's surface to not be deflected? Let's look at, first of all, our right-hand rule for deflection to see which way the force is on this positively charged particle. And then we'll go from there. You don't know how to solve this question? That's okay. Just do something. We have a positively charged particle going towards magnetic south, which is geographic north. That's that way, towards Jordan at the back of the room. So I'm going to stick my right thumb towards the back of the room, or towards Jordan. My fingers are going to go to the west. My stretched out fingers are my flattened fingers, not my curled fingers. Okay, that would be the wire grasp rule or the coil rule. Okay, the hand rule for deflection is my straightened fingers. Thumb, fingers, palm points up. So the magnetic force is upwards. Now answer this question for me. If the magnetic force is upwards on this positively charged particle, how come this positively charged particle doesn't go upwards? How come it goes undeflected if there's a magnetic force upwards? Okay? Not because of inertia, no. Inertia wants to take it in a straight line, but any force will take it out of that straight line path. Any unbalanced force, that is. Do you hear what I just said? Any unbalanced force will take it out of its straight line path. Yeah, there's got to be some other force. If there's a force upwards, there's got to be some other force that balances it downwards. And it stands to reason that since we're near the Earth's surface, that's going to be gravity, right? So that's what we're going to do here. For this question, we're going to say the magnetic force upwards is equal to, in magnitude, the gravitational force downwards. We're going to say QVB is equal to M times G. And I'm going to rearrange that to solve for V. V is equal to mg over q times b. If these two forces are equal, this is the speed that the particles need to be traveling to make them equal. All right, let's sub in our numbers here now. I got a mass of 5.00 times 10 to the negative 25 kilograms. G is 9.81. Q is 1.6 times 10 to the minus 19 coulombs. And the magnetic field strength is 2 times 10 to the minus 5, which is a pretty typical magnetic field strength near the surface of the Earth. All right, let's see what we got here. Say 5 times 10 to the minus 25. Times 9.81. Let's press equals there, and then let's divide that by, sorry, 9.87. Let's try that again then. 5 times 10 to the minus 25 times 9.81. Let's divide that by brackets on the bottom, 1.6 times 10 to the minus 19 times 2 times 10 to the minus 5. 1.53. That's pretty slow. But it's possible, right? Usually we expect 10 to the 5, 10 to the 6. 1.53 is pretty slow. Why? Well, this particle is really, really light. Right? 10 to the minus 25 kilograms. This is like subatomic scale, right? If we have such a light particle, we don't need very, very, very much magnetic force at all to balance gravity, right? Because it's such a small gravitational force. And if we don't need a very big magnetic force, we don't need a very big speed to accomplish that magnetic force, right? So that's why the speed ends up being so small. It is an unusually low speed, okay? But when you start thinking about how much magnetic force is necessary, think like, okay, that might make sense. Is that okay? Whenever you see something suspended, undeflected, not be deflected, right, going in a straight line, forces have got to balance. You just got to figure out which two forces to set equal to each other. Electric and gravity, magnetic and gravity, electric and magnetic, just depends upon the context of the question, right? Let's spend a couple minutes now reviewing what you guys did yesterday here. We have a magnetic field here. This time it's going out of the page. Yesterday, what I drew on the podcast was a magnetic field going out of the page, or into the page, I should say. It doesn't really matter. We get a negatively charged particle, let's say, going this way, going to the right. The velocity of the particle is represented by green. We know that this charged particle, since it's going perpendicular to the field, experiences a magnetic force. Which way? Well, we'd say thumb in the direction of the particle, which is towards the right, fingers in the direction of the magnetic field, which is out of the page, palm points upwards towards the top of the page. So the magnetic force is upwards towards the top of the page. Now, we could describe exactly what's going on right here using what we did a few minutes ago on worksheet number 11. F is equal to QVB. It's absolutely valid. It still is, even though we're going to go a little bit further with this now. As a result of this force, QVB, there's going to be a change in direction of this particle. If it's moving to the right, but there's a force upwards, then that means it's going to start going somewhere in between. Maybe this way. Now it's going up and to the right. There's a different force on it acting now. The speed hasn't changed, but the direction of the force has. We're going to say thumb in the direction of the particle, fingers field. So thumb this way, fingers this way, palm points this way. palm points up and to the left. Magnetic force acts this way. Now, it's going to go somewhere in between as a result of that. Now it's moving upwards, thumb, fingers out of the page, palm points to the left. Look, you can see what's happening here. You can see that this particle, as long as it's in the magnetic field, ends up going in a circle. Now, once it comes out, it goes in a straight line, right? But as long as it's in the magnetic field, it follows a circular path. If it was going faster, maybe this would be the shape of the path. Circle until it pops out the other side, then straight line. But again, as long as it's in the magnetic field, it goes in a circle. What did you guys do every time last year in Physics 20? Every time something was moving in a circle. Centripetal force, the force that points toward the center of the circle. The centripetal force equal to mv squared over r. We're allowed to do that now too. Now, we're not going to throw away what we learned a couple days ago. It's still valid, but now so is this. It's not like these questions should be harder. It's just that now we have an extra tool in the toolbox. Now we have mv squared over r in addition to QVB. Now, sometimes when you're building a house, you got one tool, sometimes you got another one, sometimes you're going to end up using both of those tools together. Usually, if a question doesn't, in this context, doesn't involve radius, we're probably just going to do that. If a question does talk about the radius of the curvature of the path, then we're probably going to do this. It's actually pretty rare that you use this by itself. It's pretty common that we use this by itself, and it's pretty common that we use the combination of them. Every once in a while, maybe this by itself. Okay? But here's the deal. If it's the context of a charged particle in a magnetic field and you see the word radius in the question, go with the third one. Start with that. If it doesn't work, then try something else. But that's almost certainly what it's going to end up being. All right, we had 5 questions for homework last night. Worksheet number 12, 5 questions. Let's go over 3 of them, questions 3, 4, and 5. Number 3 says, what's the magnetic field strength required to make a proton with a speed of 5 times 10 to the 5 follow a circular path of radius 2 times 10 to the -2? Charged particle in a magnetic field. We know that F is equal to QVB applies. That is, it applies if they're perpendicular. The field and the particle are moving perpendicular. It doesn't say that, but it does say it's going in a circle. And if it's going in a circle, they must be perpendicular. So we're okay. Right, Cody? We're okay using the equations that we've learned here. We know we're allowed to use F is equal to QVB, but notice we have a radius here. So we're probably going to use that last one, FC is equal to FM. That's at least what we're going to try first. We're going to say mv squared over r equals QVB. One of the v's cancels, right? V squared on the left side, V on the right side. One of the v's on each side cancels. And now we're solving for B. The Q comes over by dividing. I get mv over Q times R equals B. So we got, what is that? 1.67, I think. The mass of a proton times the speed of 5 times 10 to the 5. Divided by the charge, which is 1.60 times 10 to the minus 19 times the radius, which is 2 times 10 to the -2. And when you do that math, should work out to be 0.26 or 2.6 times 10 to the minus 1 Tesla. Now, number 4, a little bit different here. It says, what's the kinetic energy in joules and electron volts of an alpha particle that moves through a magnetic field strength of 1 times 10 to the -1 Tesla and follows this circular path? Again, we're not told that they're perpendicular, the field and the motion of the particle, but they must be if it's going in a circle. Never did one of these where we had to find kinetic energy. How do we do that? Don't know? That's okay. Charged particle in a magnetic field. We've got a radius. Try FC equals FM. See what happens. See what happens. mv squared over r equals QVB. One of the V's cancels. I get mv over r equals q times b. I've got everything in here except for v. So let's solve for v and see what happens. Q times b times r goes up by multiplying, m goes down. We can solve for that speed. When we do, we get 120, 300.75 meters per second. Any ideas now? Like sometimes you may not know how to get something, right? When you start the question. Look at this question, kinetic energy. I've never done that in this context. How do I do this? Do something. Do something you know. Charged particle in a magnetic field going in a circle, got R. Set it up. Get something. And then every once in a while, something comes out like this, and then a light bulb turns on and you're above your head, right? Hey, speed, mass, kinetic energy. Cody, how am I going to find kinetic energy? Yep, which is 1 FmV squared. Yeah, plug in your numbers. We got a value of 4.8 times 10 to the minus 17 joules. All right, now we got to convert that to electron volts. An electron volt, listen carefully here. An electron volt is the energy that's gained or lost by an electron as it moves through a potential difference of a volt. So an electron can speed up through a potential difference of 1 volt if it's going, quote, down the hill. It would slow down through a potential difference of 1 volt if it's going up the hill. It gains 1 electron volt of energy going one way, it loses going the other way. Okay? Now, what does that work out to be? Well, the energy gained or lost by an electron through a potential difference of 1 volt would be the charge of that electron times the potential difference of 1 volt, which gives me this. Then I say the energy gained or lost was an electron volt. The energy gained or lost is 1.6 times 10 to the minus 19 joules. That tells us that 1 electron volt equals 1.60 times 10 to the minus 19 joules. And that conversion factor is on your data sheet. But if you're anything like me, when you see a conversion for the first time, one that you've never done before, you look at this and say, okay, all I need to do is multiply or divide. You get mixed up. Do I multiply or divide? Like, I don't get mixed up on this one anymore because I've done this so many times. But I guarantee you, when I saw this for the first time, I would have gotten mixed up on it. Do I multiply or do I divide to get electron volts here? So here's what I do. When I see a new one, a new conversion that I've never done before, I just set it up as a little bit of a ratio. On my data sheet, it tells me 1 electron volt is the same as 1.6 times 10 to the minus 19 joules. Just set it up as a fraction. This equals this. This equals this. So if 1 electron volt is 1.6 times 10 to the minus 19 joules, then x electron volts is 4.8 times 10 to the minus 17 joules. Solve for x. And when you do that, it works out to be 300 or 3.0 times 10 to the 2 EV. Make sense? You can convert any unit you want as long as you have the conversion factor, just setting it up as a ratio like that. So we know that we want to, listen, number 5 says we want to compare the radius of curvature of an electron's path to the radius of curvature of an alpha particle's path. We know we want to compare two things, we divide. So let's say radius of the electron's path divided by the radius of the alpha particle's path. Now, if we know the numbers, that's great, easy. If we don't know the numbers, it becomes a little bit harder. Let's derive an equation for radius. Let's say FC is equal to Fm. mv squared over r equals qvb. These cancel, r goes up, qb goes down, r ends up being equal to mv over qb. There's the radius of the path of a particle. So let's say the radius of the electron's path would be MEVE over the charge of the electron times the magnetic field strength that the electron experiences, divided by the mass of the alpha particle, the speed of the alpha, divided by the charge of the alpha times the magnetic field strength experienced by the alpha particle. So we don't know the numbers for these two radii, but we do know the expressions for them. And that's better than nothing. We know we got to divide. And that's a good thing here, especially when we don't know numbers. Because every once in a while, when you divide things, things just cancel out of it, as they do here. We know the speed is the same of both of them. The magnetic field strength is the same. So I end up with ME over QE divided by M alpha over Q alpha. We can simplify that a little bit by multiplying by the reciprocal. We're going to say ME over QE times Q alpha over M alpha. Do the math. Do the math. And when you do, you get a value that is 2.7 times 10 to the minus 4. Well, if the ratio of my age to Nico's age is 2 to 1, and we got that by dividing 36 by 18, 2 to 1, then the ratio here would be 2.7 times 10 to the minus 4 to 1. When you divide the two numbers, you get the first number of the ratio. Yeah, Nick? Good question. How do you know which one's on the top, which one's on the bottom? Okay, so let's find the ratio again of my age to Nico's age. My age to Nico's age, divide my age by Nico's age. If you wanted to find the ratio of Nico's age to my age, it would be 1 to 2, right? A half. So it would be 18 divided by 36, right? Now in this case, we're trying to find the radius, how the radius of curvature of the electron's path compares to that of the alpha particle's path. How does the electron compare to the alpha? We're going to say electron over the alpha. Okay, make sense?